So my background is physical engineering, and I've been going into that space of nanotech since the mid-90s. I had a field of research within extraction of electrons out of carbon nanostructures, new type of solar cells, and new type of data storage systems. So this is how I get familiar with that world of the nanotech. And we heard from Christine the definition. What was for me in evidence is that the convergence of biology, chemistry, and physics, giving this field of nanoscience, was of great potential. And why is it of great potential? I mean, think of what we've been doing as humanity. We've been playing with the things around us. Wood, stone, steel, and we are going smaller, molecular medicine, integrated circuits. But what is the most relevant for humans are the atoms. The way you control them, the way you assemble, the way you put them in 3D. So the way we've been looking at that space of nanotech as a practice, we've been seeing two trends. One into the physical science nanotechnology, basically applying semiconductor technology on your substrates, and the other one, which was life science, where we combine biology and chemistry for those self-assembly systems like nanoparticle. So that is my slide. The rest is going to be just example. As some of the company now are public company, I have to state that what I'm going to say today is I, the CEO and founder of Nano Dimension, I do not act here on behalf of those companies. The first example is View dynamic glass. And the idea behind that technology in the physical science space was, can you create a glass that you will tint on demand? You will control the amount of light and heat that you let go through that systems. So that was the idea, a migration of ion within nano metal layers embedded into the glass, where by charging those layers, we will be able to control on demand the quantity of visible light, infrared, and UV that we let go through. Great idea, right? We can save quite a lot of energy consumption of building while increasing comfort. So how did we start? We started with chemical vapor deposition, typically nanoscience, whatever you have into a university. And out of this, we've been able to do small samples, a few millimeters square. And we've been able to tint that, interesting as a science. But now to move from science to technology, we have to scale it up. This is how we did the intermediate step. This is about $60 million of CapEx. And even just here in Silicon Valley, where you have capital available, just to try to bet that we're going to put that amount of money to try an idea and a science to scale up, you don't find those capital. The reason why we moved here is because this is available. This was a hard drive disk coating line. We've been able to repurpose a hard drive disk coating line to now start to do deposition on glass. And with this, we've been able to develop a technology and being able to understand scalability. From there, we could move to this, a 500,000 square foot facility employing 500 people. And this is what you have today. This is the plasma chamber, the largest plasma chamber in the world, 275 yards long, and 15 feet high. And we manufacture high volume glass that tint on demand. This is just a reality. You heard about before definition, what we can do. This is a factory, 500 people. And we ship that glass. So let's look at some installation. This is commercial real estate, and you see the glass that's going to adapt in order, in that case, to make the room comfortable, increase rent, and increase renting duration. This is corporate headquarters. You see the phase change of those glass, and this is increased comfort. Here you see even a church. And for what? For view and comfort in that case. You have a hospital. You have here a hotel for comfort and premium effect. University, you work better under natural light. You heal better here in the case of a hospital under natural light. So we have now deployed about 250 buildings. We have about 150 into the books, and that company is in a growth. So if you just drive down to the Bay, this is the headquarters of Netflix. You see building 1 and 2 done traditionally with blind and shade and low E, and building 3 and 4 are coming with view glass, and you immediately understand the difference. I don't lose the view. I save up to 20% of energy. I increase comfort into my building. Moving now to the other spectrum, we look at application of the physical science. Let's move to the nanomedicine. And the first example I'm going to take is the usage of nanoparticle. Before going into Selecta Bioscience, I'm just going to basically introduce the system with what's happening, like in the example in case of hemophilia. You familiar with hemophilia, you miss a protein called factor VIII, which have your blood to not coagulate, which means that if you have an internal hemorrhage or a cut, you're going to bleed to death. And well known because of the Romanov, the Tsar of Russia, that was carrying that gene deficiency. So you miss a gene to produce that protein that is so important into your system. So over the years, humanity has been able to synthesize that protein and inject that protein into the system. Now, if you take an aspirin, it's a small molecule. Your immune system is happy, you feel better. But when you start to bring enzyme, protein, those biologics, they're going to be seen as potential intrusion. And what your dendritic cell is going to do, they're going to basically decide if this is an intruder or if it is a good guy. But in the case of hemophilia, about 20% of the people injecting factor VIII protein, they're going to be having an immune response where the body is going to generate antibodies that's going to get and block that protein. So they need it, but the body blocked it. So that's a problem. Now, what would be great with gene therapy is instead of just injecting the protein, you could actually inject the gene. And the way you do it, you put that gene with a virus, that virus navigate in your system, deliver the gene very efficiently into the cell. But what you have is, remember those dendritic cells, they can look at you and decide if this is good or bad. And when you come with a virus, if they don't know the virus already, next time the virus shows up, it's going to be stopped. And the problem with gene therapy is exactly this one, is you can inject only once. Or deficiency is when you're a young baby, or as this baby grow up, if you inject within a young child, later on it's going to need more genes, and at that time, you have antibodies going to neutralize it. So what do we do with Selecta? The hero of the story is that nanoparticle. That nanoparticle is able to communicate to the immune system and tell the dendritic cell, hey, whoever come with me is a good guy. Don't send your troop. Record that information. So when he shows up with a biologic, basically that biologic can act, and we don't have immune response. So let's take an example. And those are human data. This is not animal, this is not theory, this is human data. What you see here is in the case of gout disease. And gout is, you're familiar if too much champagne and too much white wine can get you about those kind of things. And above a certain level of uric acid, you're going to start to create crystal that's going to go into your joint. And it's painful, and there's a lot of morbidity associated with gout. This enzyme is very good to go and grab those crystals and drop your level of uric acid. This is what you see. You inject the enzyme, but after a few days, the level of uric acid goes up again. Why? Because the antibody have neutralized that enzyme. When you send the nanoparticle alone, no effect. When you send now the nanoparticle with the enzyme, you see a completely different type of profile. So those are human data, very exciting human data. And I can mention Selecta released it. Selecta is launching 2 gene therapy programs, hopefully to show that we can achieve the same by partnering that hero with additional program. Immunogenicity is not a small deal. Okay, there's about 100 treatments today where when you read the pack, you're going to see that you have immunogenicity. 36 of those programs have more than 20% of the patient that cannot tolerate those treatments and create antibodies. Humira, #1 selling drug in the world, 12 billion is one of them. So it is addressing an important problem and potentially can lead to additional stimulation program. So this was 2005, 2010, okay? So what we saw first was a convergence of science. With those technology developing, what we've been seeing is that we were getting a set of tools that were not just university. We passed university. You see, this is factories. This is hundreds of people. This is product into the market. We have tools now that we can use, and we can combine them between physical science and life science, and that accelerate what we can do. This becomes application engineering, and the speed of which those companies are developing is increasing. We still have continued to do investment in physical science space, like new type of battery, or Armo Bioscience, which is an immuno-oncology company And in this case, we have about 350 patients in trial today with extraordinary results in pancreatic cancer. So we're going to move to a phase 3 trial early next year with that company. I will not mention about Armon or Alveon or about an additional dozen of companies we have. I would just focus on 3 examples where we have that convergence. And the first one I'm going to take is Pulse Therapeutic. So Pulse target a problem which is the #1 spending in healthcare in the US, which is long-term disability following blood clot in the brain. Disability of patient having suffered a clot in the brain. You lose about 1.9 million neurons per minute that part of the brain is not irrigated. Today, if this happens, you have good way to do it, which is exactly like plumbery. You need to go into the vein, unclog it with a device, and take it out. You can do that here at UCSF or Stanford, but if you're not close to those centers where they can operate only within 4 hours, then you have a significant problems. And this is less than 5% of the 800,000 brain clots that happen every year in the US that are being treated. This is about 15 million people per year in the world. Countries like Britain don't even do those kind of device in order to go and unclog the brain. So the idea here is, can we use nanoparticles that are small enough that we could direct into the brain and activate them with a magnet? The magnet will be less than $10,000, and the treatment less than $50 to produce. Now, what you do have is, when you have a clot, basically the fluid takes the easiest path to go. And that clot doesn't see a protein that we have in our body called TPA that is very good to go and unclog. Now, what you see is here in that model, you see on the top just TPA, that drug, actually, it just doesn't make it to the clot because simply there is no fluidity, there is no movement. This protein, so well needed on the spot, do not get to the place. Now, when you move with an unoptimized version of those nanoparticles, you see that in 15 minutes they've been able to do something, and with an optimized one, you can potentially clean it up. So those are as well human data with the unoptimized one. 7 patients, out of those 7, 5 recover and get canalization through. 5 out of 7 with the unoptimized one. With the drug TPA today, you have less than 5% chances to have recanalization. So there is good chance that we can do something, and we're going to move to a large human clinical trial later this year with this company. The next company I'm going to mention was one of the largest spin-off, I think, of Harvard history, when we took 28 scientists out. And what they wanted to do was, just by looking at how we do drug discovery, we use and sacrifice about 100 million animals every year in the US only. A monkey costs about $30,000 for pharma research. So it's a lot of animals being sacrificed. It's a lot of money. And you have less than 4% that what works in animal works into human. So it's a very poor translational model. So the idea here is, can you use human cell, build up chips that are dynamic, that will represent the major organs of the body, and in that case be a better model than animal model. So that's the idea. So here's the lung chip. And what you see into that lung chip, you will see, as it is a lung chip, a cavity and a channel for air, cavity for blood with a membrane that split the two. Now you're going to grow human cell, lung cell, capillary cell. You're going to use human blood with all the immune system into that blood. And you're going to flow air, including bacteria. And what you want to see is, you want to see the white blood cell going across and basically blocking those bacteria. And this is what you see into that chip. You see the white blood cell. And when you get the bacteria, the white blood cell go across and neutralize those cells. So now this becomes interesting because you can now inject the drugs and see the mechanism of action and directly what's happening with that drug. So IL-2 is a interleukin-2, was a oncology program that unfortunately all the patients in that trial died. as the liquid split between the blood and fill up the lungs. This was not foreseen into animal models. We could see that into that chip. So this company is now 2 years old. We shipped the first systems not only to pharma partners and university, but as well to hospital. And this hospital partner is particularly interested to take the human blood cell of the patient, load it onto the chip, and run those heavy treatments on the chip before they go into the patient. So they can, those cocktail of drugs, they can now see the effect directly onto the chip with the cell of the patient before going into the patient. And this is basically the ultimum of what personalized medicine can do. The next company, and we heard a little bit about DNA and how DNA is important. The next company is a DNA printing company. So you design your sequence on your computer, you send the sequence, we print it, we ship it back to you. That's what they do. Now, do you say, why do I need DNA? Well, DNA is quite an important opportunity. As you know, it's a software of life. And based on what the cell or the bug is being programmed, now you're going to have sugar coming in, being metabolized, and produce whatever you want. So carpet, tires, meat, silk, today are already being produced by fermentation. You feed the bugs with sugar, you produce whatever you want. This is synthetic biology. It's called industrial biotechnology. It's happening. The next one is, of course, gene therapy. You need gene. There's plenty of things to be done with gene. I'm going to mention one that you're going to find a bit futuristic, but it's very real, and we're on the contract, and we're shipping it. It's data storage. When Boeing has to do storage of information, when they build up a plane, it has to be lasting for very long. I mean, 20, 30 years. Anything that has been produced on that plane has to be stored. And they do that how? In tapes. Or tapes, magnetic tapes, do not last very long. DNA lasts millions of years. So Microsoft, which is the #1 storage company for long-term storage, is ordering gene, and instead of 01, is your 0123 ACGT. And now they send us a picture. We move, instead of 01, we move in 0123. We print the gene, we send back the gene, they sequence the gene, and they reconstruct the image. And you have 100% transmission on the information. So interesting here how gene can be used if gene can be cheap enough. So how does it work? You have a plate, and in those plates, you're going to bring your oligo, your 4-element, ACGT, in just one cavity, and you're going to have 96 of those cavities. From there, you're going to extract that sequence that you just assemble. You put it together with PCR, polymerase chain reaction, you're going to form your DNA. All basic technology, this is 1983. So all this worked very well. Now you click it onto the vector, the virus, the same as you use in the case of bringing a gene for hemophilia. And now you have that gene into the cell. Now that cell, fed with sugar, is going to produce what the gene tells it to do. So this is how it is done today, those well plate, 96 well plate, to make one gene. What we did is we moved that now into silicon. On the same surface now, you do 10,000 genes. So 4 orders of magnitudes. Instead of doing $100 revenue with that plate, now you do $1 million of revenue on that same piece of silicon that takes the same times and the same amount of reagent. Now you break an industry. The company, 3D printer, the printer are live and starting to ship gene last month. First quarter, 1 million revenue, and it should be now exponential growth. To conclude with my same slide, the 5 companies I showed you, it's over $1 billion of funding. Okay? So this is a place that venture capitalists come in. We have sovereign wealth funds following us. There is state pension fund. There are growth equity partners. As you see, those are significant opportunity in terms of what is the trouble that we try to solve, the entry barrier that we create by not only the 400 patents that is associated with view, but as well the CapEx and the manufacturing site, and just by taking the market before anybody else. What I find particularly stimulating in all that is the gross margin that you can have associated to all those breakthroughs. So nanotech is enabling, in that case, a tremendous breakthrough in order to come and conquer industry that have not evolved for many years. And I believe that out of this space, you're going to see some significant blue chips that is going to emerge. Now, you ask me, okay, what's next, okay? And why is it a good place to go? The first thing is, look at what you have. If you look at the industry, which is as well the financial and investor community, the IT guys, Google co-invest with us in immuno-oncology. Why? Access to data. Microsoft buy Gene now for data storage. And you have the same with the pharma guys that goes into now microfluidic or use mass spectrometry that is a tool of semiconductor to basically do mapping of protein to enhance immuno-oncology. So all this mess that is happening that nobody knows what is going on, qualified as the fourth industrial revolution in Davos, is really what the power of the atom, the way they organize, and that they are so converging that you unlock unbelievable opportunities. So the buyers that you have now in one sectors is not just coming out of the sectors, but you have multiple buyers, multiple industry being attracted to those technologies. So I'm bullish long-term of what's going to happen into that industry. So what's going to happen next? I think that when you see View and the way we can digitalize the business, where we not only sell the glass, but you sell the glass and after you want to use it and activate it, it's data, it's services, you're going to pay recurring income. The data that you get out of this chip, the organo chip, in order to do prediction of, do I need to stop a program of development of that drugs, or how do I have to treat that patient? Because I know now I have millions of patients and I know better what kind of cocktail of drug I have. Data of those nanosystems going to become extraordinarily relevant. The next thing that we're starting to look in detail is the combination of nano with the first investment into the brain with no particle, combined with the cognitive. I think this is something that's going to take some time, but it's going to be very interesting. And I will not be surprised that within a decade or two, the keyboards that we have today for our computer is not there anymore, nor the steering wheel for our self-driving car. And there's going to be a lot of new interaction that's going to be taking place.